it will be automatically added to the path NVIDIA C compiler, NVIDIA C++ compiler. We can see its version. I will show you practically. Okay, let me go to the command prompt. Right. Uh, so, as CUDA kit toolkit is already installed into this PC, so we can check its NVIDIA C compiler. We can check its version by this option NVCC-V. Right. So we can see that we have I have installed on this machine NVIDIA CUDA compiler driver, right? The copyright year, right? And its version that is important. That is the version is 10.1, right? So I have installed 10.1 version because it is compatible with my graphics card. So that is one important thing you must see while installing the CUDA card. Sorry, this CUDA toolkit. You have to see that which CUDA toolkit is compatible with your card, because if I the latest version of CUDA toolkit is 12, right? But it is not compatible with my card, that is GeForce GT 740M. So that's why I installed the previous version of the CUDA toolkit, that is the version 10.1, right? So uh, once we have installed the CUDA toolkit and checked whether it is installed properly, no, what are the other contents of the CUDA toolkit? It contains the, just a second. It contains NVCC, C++ compiler, right? Then it has different libraries like CUDA FFT library, Kublas, that is the library for basic linear algebra, subprograms for linear algebra. These are different libraries. Then it has a profiler. So profiler is basically tool to see the timing, to study the timing of execution of a different part of our code. We have different parts in our code or different statements. What is the timing of execution of different type of data transfers or execution, that we can check through profiling by profiler. Then this is the alpha version of GDB debugger. I have not gone through it anyway. So now then it has a CUDA runtime driver, and then it has a CUDA programming manual, right? These are the different contents of our CUDA toolkit. Now, what is the role of the NVCC compiler? As we discussed earlier, basically our code is made up of two parts: the serial part and the host part and the device part, right? So NVCC compiler will partition the code into the host code and into the device code, right? For example, we have a file over here, mycuda.cu. So cu is the extension of the CUDA file, just like C is the extension of the C file and CPP is the extension of C++ file. In the same way, cu is the extension of the CUDA file, which will be writing our program, right? For example, there is a main function, right? There is some variable of declared into the shared memory. Then there is a uh, so we have this main function, sorry. So this is the main function. So of course our code will contain the main function, and then this is the global underscore. This is the kernel function. A kernel function is identified by the this underscore global underscore. Okay, I will just for the time being in this slide we focus on the serial part and the parallel part, right? So serial part is shown blue, right? This is the host part, and the part which has to be executed by which has to be compiled for the device, that for the GPU, that is in this part. So NVCC will compile this part, and our host compiler, CC plus compiler, that will compile this part, right? So NVCC will divide into these two parts, and then also combine it both together. Now we come to the CUDA development tools. What are the development tools we need, right? We may need different. We need integrated development environment for our CUDA C++ based application development. We can have any IDE. We can have Visual Studio. We can have Eclipse. We can have Qt Creator and Designer. And here we will be using Edit Plus for the time being as a general purpose editor, and in this we can configure for compilation and execution of our code, and there are many more IDs are available, right? So whichever ID you use, you will have to configure the CUDA compiler and CUDA libraries in your IDE. If we talk about Visual Studio, when we install the CUDA toolkit, if the Visual Studio is pre-installed, it is automatically configured into the Visual Studio, right? So, should we take some break for some time? Or, hello, am I audible?
Yes, Vikram, we can hear you. You tell us
I think we
how
should
long.
have a break of 10 minutes.
Okay, sure. Time is 10:26 here.
10:26.
Uh,
We can start at 10. You suggest 10:36 or 10:40?
okay, 10:40. That
Fine.
would be, I don't know what time in San Diego. Let me check. Like 15 minutes from now. Okay, sure.
Fine.
Okay.
Thank you. Hi everyone.
Hello, Vikram.
Yeah, hi.
Yes, we are back. If you can start
Yeah.
when.
Sure. Yeah. Uh, yeah, as we have discussed on the previous slide regarding configuring the compiler, C compiler for the host code, right? So, so that we have to see whether it is appropriate compiler as per our machine or not. We have selected. We should select that much that compiler. For example, in my machine over here, the C compiler is for host code is the CL, right? I hope everyone is able to see. So this is for x64, right? So I have configured this CL compiler x64 version in my path, right? So if you are using Visual Studio, then it is a different issue. But if you are using any editor and configure the compiler in that editor, right? Then we should set our appropriate compiler in the path. Should I show how to set the path? Or I think everyone must be aware of this.
Yeah, I think we can skip that part.
Okay, fine. Right.
Can you share some links as to how to do it for Visual Studio?
Sorry, I'll
Anyhow,
Can you share for how to do it for Visual Studio?
no, Visual
So,
Studio will
Vikram,
be.
can you share any link for that? I think they'll be able to take a look at it. That's what they were asking.
No, it's okay. That is the only part I had explained. Only just we must see that we have configured the compiler in the path. If there is any issue, then we can discuss. I don't know that how many people will be doing practically on their machine. So whenever they will find any issue, then they can discuss with me, right?
Yeah. Now, Vikram, also a small request.
Yeah.
So, since many of them are not able to use their mics, they've actually posted their questions in the chat. So maybe if you can collect them at the end, and
Yeah,
we
sure.
can just in the
I,
back, and we'll just have answers to each of them later in one, if that could be helpful then.
yeah, sure. That will do. No issue.
Okay, thanks.
Okay. So once we have, so this was last part, means CUDA development tools. So once we have set up our machine for CUDA development, right? We have all the facilities available. And for example, if I want to show about this edit plus, okay, edit plus I have in my machine, which I am using for the time being, right? I would like to show it. uh, Edit plus, right? So in this, this is a simple editor. For example, I can open any file into this. For example, if I open a file test1.cu, this is the CUDA file, right? So just look like a simple C file, right? So here I can configure user tools, right? Here I can, for example, CUDA compile. For the first option, it is the CUDA compilation, right? So CUDA compile, then we can see that these are its options. It is just its name. Then what is the command? Command is NVCC. I can browse the command and select any command from here. And here I have just put NVCC, right? Because NVCC automatically has been set by CUDA toolkit into the path. So I can just type NVCC instead of giving its full path over here. Then its arguments, I hope it is visible. File name, we have to give its arguments file name minus o, that is output, and then file name without extension. Anyhow, so anyway, we will just go through it in detail when we will actually doing it practically. Now coming back to the CUDA programming basics, right? So to compute for we need to allocate so what are the different steps in our program we have to do, or what are the major steps in our CUDA programs? First of all, we have to allocate memory that will be used for the computation. That is, we have to declare the variables and allocation, do the memory allocation for them. Then we have to, if there, for example, if we have a large array, we have to declare it and allocate memory for it, and then write the data to the device memory that we will compute on. Then we have to transfer this memory to the device. We have to create it on the host. Just a second. Yeah, we have to create it on the host, and then we have to transfer it to the device. Then we have to specify the computation that will be performed on this data, and then we have to read back the results from the device. We will see it graphically. So for example, there is an array we have created on in the host memory. We have created an array, and this is the GPU card. So we have to copy this uh, array from the host memory to the GPU memory, right? So here it is named as the array, and here it is named as the array underscore D. That is for the device. D is for device. So what we have done here, so this is the very important step, that is we copy the content from the host memory to the GPU card memory, right? Once the data is has been transferred, so that was the first step, transferring of the data, right? Once we have transferred the data, then we execute the code on the GPU. That is their GPU multi processing units, GPU multi processing units. They will process on this array in parallel. So once the computation is done, we have to copy back the results to the host. So array underscore D will be copied back to the host.
Hi Hi Vikram, am I
Yeah,
audible?
yeah. Hi.
Oh, Uh, one question, one small question. So, when you say when we copy the memory from host to the device,
Yeah,
then there is some CUDA API that is in doing the work there, or
yeah.
uh,
There's the CUDA API is doing the work there. Yeah, I don't know
okay.
why
I was just wondering if we.
this slide is, I
Mhm.
suppose, is not going properly. Let me see. There's some problem.
Yeah, there is some glitch.
There is some glitch. I think CPU is has hung, I suppose. Let me see. It's a Microsoft Office. Yeah, it is slow. Let me see. What is the issue? I don't know. There's some issue on the PC. Let me see. It is being displayed pixel by pixel. I don't know what is the issue. Yeah, yeah. Please repeat your question. Yeah. Hello.
Yeah, hi Vikram.
Yeah, yeah,
So I was just asking, you confirmed it, right? So we have a CUDA API which
yeah,
copies the
yeah,
memory from allocated on host to the. So we are able to access the memory that is being allocated to the GPU card, like a normal pointer, like we do it on the host side. Is it
yeah,
the
yeah,
case?
yeah. We can do that. Yeah. If is it?
Then I
Yeah.
think,
Hmm.
hmm,
Yeah, yeah.
yeah,
Please.
it's visible now. I think.
So if I is it okay if I run it in this? It is not slideshow mode. Is it okay? If I is it visible? If I do not run into slideshow because there is some glitch coming when I do it in the full screen mode.
So Vikram, let's continue what works for you now. We'll see
Okay,
if
okay.
that improves. Then we can get back to full
Yeah,
chat.
yeah, yeah.
Thank you.
So we are coming to the next CUDA kernel part, right? So CUDA kernel, the computation part, as we discussed in the previous slide, the CUDA kernel part, right? CUDA kernel is uh, executed on the device. This is the computation which has to be done on our data, right? So code, this is kernel is the code which has to be executed on the GPU that is written as the CUDA kernel. These are the data parallel portion of the application which are executed on the device that is GPU. Kernels run in parallel in on many threads, right? Now regarding the grid size and the block size, programmer it is the programmer who has to specify the size of the grid, right? The programmer has to specify the grid size and the size and shape of the data that the program will be working on, right? The programmer has to specify the block size. The block size indicates the sub area of the original grid that will be assigned to an multi-processing unit. right? So multiprocessor is basically a set of stream processors that share the local memory that we will discuss in a bit detail. Now regarding the block size, the stream processor, as in the previous slide we saw its a bit reference, right? The stream processors of the GPU are organized as multiprocessors. And this was the question I think we were discussing about earlier also regarding the cores, right? Stream processors are organized as multiprocessor, and every MP has its own set of resources like registers and local memory. The block size needs to be chosen such that there are enough resources in an MP, that is multiprocessing unit, to execute a block at a time. So in the GPU, we have processing elements. We have multiple threads. For example, we have this is the block 0, and then we have block 1. We have then thread 0, thread 1, thread 2, thread 3. This is for first block, that is block 0. And every thread we can see that is working separately on the array element. Just a simple example. For example, we have to do the array addition of 1 million elements. If we do it in serially, we will be performing operation on the first element, first set of elements, then second set of elements, means the first index, 0 index, 1 index, and 1 million elements. So our loop will iterate 1 million times. So 1 million times. So that is the serial execution. But if we do it in the parallel, all the 1 million elements, they will be processed simultaneously if we do it into the GPU computing. So all the elements are processed simultaneously. This is which is being depicted in this slide. So different threads are working simultaneously on different elements. They may be from different blocks, right? We have a one array of say 1 million elements, and different threads from different blocks and different grids, they may be working on these different elements for simultaneous operation on all the elements together. Now this is a basic CUDA C example program, right? Just here we have included a header file CUDA.h. Then we have included the file stdio.h, right? Here we have written a, so this is a one thing we see, we must see underscore underscore global underscore underscore. So this is a function that is to be compiled to run on the device. So this is our parallel program basically, or the kernel program, which has to be run on the device that is on the GPU, not on the host CPU, right? And how it is called, for the just simple program, this is just empty. We have not written anything in this kernel program, right? It is identified by this you can say identifier underscore underscore global underscore underscore, and its return type is void, and name of our kernel, the kernel over here, and if any argument, right? So this is how we invoke it in the host code, how we call the kernel, right? So this is the name of the kernel program. Then this is the three angular brackets, right? Opening brackets and closing brackets. So these are some arguments. Basically, this is we specify first argument is the number of blocks, and second argument is the number of threads within a block. So number of blocks in a grid and number of threads in a block. So we will see in detail. So in this program, we are just displaying a message. So as of now on this slide, we must see only these two main points, underscore underscore global underscore, that is to identify a particular kernel. And when we have to invoke it through the angular, three angular brackets, opening and closing.
So Vikram, just a question. So if I have multiple kernels, in that case, we just declare one more function using the global keyword,
Yeah, that we can do.
say global void
Yeah, that we can do.
kernel 2 or something like
Yeah,
that.
yeah, that we can do. We can launch multiple kernels.
And
Yeah,
and each kernel will be mapped to one grid, right?
yeah, yeah.
Okay,
That's
thank
right.
you.
Is this equivalent to the two device we function call we do in Python, where we like do this transform this processing to device and specify the GPU number?
Yeah, it can be done in
This
Python.
global.
Yeah, it can be done in Python also.
Okay.
But in this presentations, in this session, I suppose we are focusing only.
No, no, I'm asking
Yeah, and that's right. That's right.
like in Python we can do, but in Python we do it like we call that dot to function whenever
Okay.
we
Okay.
want to pass any tensor or anything on GPU. So is it equivalent to that
Yeah, yeah,
global?
yeah. We can do that. So just coming back to the CUDA C example program, we have a simple program to add two numbers, right? Uh, so this is our just a second. This is our kernel function, right? Identifier underscore underscore global underscore, and return type is void, and name of our kernel, and these are three arguments: A, B, C, and pointer C, right? So here in the main program, we have created a C variable and then a pointer variable, dev for the device. So regarding this part, as we discussed, we create values on the host, right? In the this program, A and B, these are the simple values, simple arguments. We are passing the values 2 and 7 only, right? So this is the just as we discussed earlier using of CUDA API. So CUDA malloc function we are using equivalent to malloc function of the host C compilers. Here we are using malloc function, right? CUDA malloc. CUDA malloc is to allocate the memory on the device in the global memory, right? So this is its syntax. Uh, we void double star, and then we have to pass the address of the pointer and how much size of memory we want to allocate, right? For example, presently we are working on single element only, so we are just reserving only size of int that may be around 4 bytes only, uh, and the pointer is dev underscore c for the device. After this we are invoking it, name of the kernel, and then the triple angular brackets we are passing the number of blocks, and number of blocks is just one, and we are passing number of threads within block again one, right? So by this CUDA function, our program will be executed, this CUDA kernel will be executed, and then we use another API to copy back the result from the device to the host, right? CUDA mem copy, that is the function we are using here. CUDA mem copy, CUDA mem CPY. That is for transferring of data between host and device, right? So just uh, I'm showing the program just to show you the basic CUDA programs, right? First of all, we are pointing the destination pointer, then the source pointer, then how many number of bytes to be transferred, and then type kind of transfer. For example, here it is the CUDA mem copy device to host. That is, we are transferring data back from device to host, right? Then we are printing back the results because the value is being copied back into the C from dev underscore C. Yeah. After this, we have to free the memory on the device, that we can again we are calling the CUDA function CUDA free, and argument is dev underscore C, that is the freeing memory on the CUDA device. So this is a basic, just to give you an idea, the basic CUDA C program.
So Vikram, just a query here.
Yeah.
So, so the arguments A and B, right?
Yeah.
So, do they go into the target, into the device?
Uh, yeah, they go into the device. They are declared into the
So,
device registers.
right? Yes. Okay. So it's because register variable it becomes.
Yeah,
That's
yeah,
why.
yeah, yeah.
Else you need to allocate it as a
Memory, local.
CUDA malloc.
Yeah, CUDA malloc. Yeah. Now, what is the?
Yes.
Why is it a register variable in this case?
Just one.
Well, I think if they single, if they are if they are single element, no, they will go to registers only. If there are large arrays, then they go into their local memory of that particular block or thread or grid. Anyhow, it is just the basic idea. We will discuss in detail about in which location different variables go in subsequent slides. As I told you in the beginning, this first slide, we can say it is just like trailer. You can say like it. I have covered all the concepts, just basic of all concepts in this first presentation. And in subsequent presentations, there's the details of different concepts. So that is the way I'm going. So now coming to the CUDA execution flow, right? Now, as application start execution, CUDA's compiled code runs like any other application. First of all, it will begin like any other application because its primary execution is happening in the CPU only. CPU is the one which will start its execution, just like any other code or application, right? Now, what happens when a kernel call is made? When kernel call is made, application continue execution of the non-kernel functions on the CPU. Means kernel call is made, okay, it is asynchronous call, means concurrent call. Kernel, once kernel is called, it keeps on executing and then CPU will go to the next statement. It can go to the next statement. Naturally, it goes to the next statement. So means CPU continues its execution after the subsequent statements after the kernel. Now in the same time, kernel function does its execution on the GPU. This way we get the concurrent processing between and CPU. So this is a concurrent processing between CPU and GPU, right? So memory move or memory transfer between host and device is primary bottleneck. So main bottleneck in of our this porting over application from CPU to GPU, the bottleneck comes at the time of data transfer between these two entities, between host and device, right? Execution of the both is halted while the transfer is taking place. While the transfer is taking place, the execution of CPU as well as GPU is halted during the data transfer, right? Now, regarding coming to the CUDA error handling, right?
Okay, one question.
Yeah,
Um, um, while pulling the data back from the GPU,
yeah,
should we have some barrier instructions or API calls to make sure that the GPU finish its job?
yeah. I
In
do.
the previous example,
Yeah,
okay.
we do have these statements or APIs functions are
Okay.
available. Yeah,
In the previous, the simple example for add, we assume that as soon as that
yeah.
kernel, it finishes in one cycle. So by the time we move the data results, GPU would be done.
Yeah, yeah,
Uh,
that
is
we have assumed that because it was just single data, so we just assumed
okay.
it that it has been done, right? But otherwise, we
Okay.
must wait. Otherwise, we must wait till the time results. Uh, we should wait that it should the kernel should complete its execution, and then only we should get back the results from the device back to the host.
Okay.
So
Okay. And there are specific functions,
yeah,
API process,
yeah, yeah, specific.
external wait, this wait for this. Okay.
Yeah,
Okay.
these are
Okay.
available. Yeah.
Okay. Thanks.
Now, a brief about CUDA error handling. CUDA for non-kernel CUDA calls, that is for the synchronous statements. Here I'm using the term synchronous and asynchronous. So I will just like to mention kernel can be called as a asynchronous function, and memory transfer functions, they can be called as the synchronous or the sequential functions, right? So so the CUDA error underscore t, it is the enumeration type in the CUDA, which is used to which holds different error codes basically, right? It is returned by all functions, uh, right? It is CUDA error underscore t is returned by most of the CUDA functions to reflect if there is any error in its execution, right? And this is error code, and it can be converted into the human readable description by this function, that is CUDA get error string. It is return type is the character star, that is we can get the string back, CUDA get error string, and we have to pass the error code and it will give its description back that we can display in our code, right? CUDA also provides a method to retrieve the last error of any previous runtime by this function CUDA get last error, right? So this was the answer to the question you have asked, how to wait till the time kernel completes its execution. That is by using the function CUDA thread synchronize. It is to block for all the kernel calls to wait till the time kernel call completes, right? So this is a function to synchronize, and it will wait till the kernel completes its execution, right? But it is of course it is quite you can say costly function, means it will halt the CPU execution further till the time the kernel is not completed. So these are the different just basics of different libraries which are available, like thrust library, kublas, that is for linear algebra, linear algebra operations. Then QFFT in the use in the signal and image processing. This API, different APIs, different libraries which CUDA have. Just I will skip this part. Different programming languages we can use, like C, C++, Fortran, Python, uh, and .NET, and many other platforms are can be used for this. Then NVIDIA also provide a visual profiler. NVIDIA provides visual profiler, which in which it is a cross-platform performing performance profiling tool. It delivers developers vital feedback for optimizing CUDA C++ applications. Means we can see that we can see the timing graph of different execution of different parts of our code, like data transfer statements, then the kernel execution if there are multiple kernel, because it is concurrent execution of different kernels, and we need to see that when one data transfer is taking place and when some other data transfer is taking place, host to device data transfer or device to host transfer. So we can have visual timing graph in this by using visual profiler, which is basically integrated into the this Visual Studio on Windows, and in Eclipse in the Linux. In the Linux, it is integrated into Eclipse, and in Windows, it is integrated into the Visual Studio, right? So NVIDIA tool Visual Profiler is we need not to install it separately. It is automatically installed, or it is the part of the CUDA toolkit only. It is a part of the CUDA toolkit. So this is just of a graph, just example of output which we get from visual profiler. For example, mem copy. This is the mem copy H2D transfer, mem copy D2H transfer. This is a different context. We will study it. What is meaning of context? This is for particular device, multi GPU. If our device, if our machine have multi GPUs, CUDA profiler will show the profiling for each GPU separately. So we can see what is the timing diagrams of our different statements. NVIDIA Nsight, it is a development platform basically for heterogeneous computing developed by NVIDIA. It can be integrated. This is the IDE basically, NVIDIA Nsight. This is the integrated development environment in the Windows platform is integrated on the Visual Studio, and in the Linux it is integrated in the Eclipse. It includes development environment and debugging tool and for the visual profiling, NVIDIA Nsight. It helps develop applications which can fully optimize for performance of CPU as well as GPU. So it is just a screenshot of this IDE Nsight, and profiling we can do into this, or debugging of the code. Now some limitations of CUDA, like it is no support of recursive functions. Any recursive function must be converted into loops. So main thing is that we have to handle the latency between of the data transfer between GPU and CPU. That is the main bottleneck for many applications, right? And then threads should only be run in the groups of 32 for the best performance. So that we have to take care that the number of elements we are processing arrays, that should be the multiple of 32, or that conversion we can do, and it is only supported on the NVIDIA GPUs. I think MATLAB part is not required. I think we should skip this part.
So Vikram, for the memory transfer latency limitation,
Yeah,
is there any technique or workaround for that?
yeah, there is workout that we will discuss. Yeah, there are workouts for that. So I think in this slide, particular later on, we have for MATLAB. I think is it required MATLAB for this session, or we should go to next part then? Right, fine. So for the timing, I skip the MATLAB part, right? So I want to show the specifications of this GeForce GT740M, the card which is available on this machine. Anyhow, this is not clearly visible. I will show it through program. Should we go with the Amdahl's law? Hello. Yes.
Yes,